Hello and welcome back to the Oxford Online Maths Club. My name's James and today I'm joined by Nang Nang.
Hello.
Nang Nang's a graduate student at the University of Oxford. What are you studying?
I study mainly probability theory. So
Brilliant.
you take graphs, you make them random. That's what I study.
Random graphs, fantastic stuff. So if you're joining us for the first time today, this is an online maths club where we do maths problems and show you maths theory. It's free and on the internet for everyone. Anything could happen because we're live. There's a chat box below that isn't on YouTube. It's on Slido.com. If you head over to Slido.com and use the event code OOMC, then you can join in with the live chat. Let's see what's coming up today. Okay, slightly different technology today in an attempt to not fry my computer. Let's find out if this works. Coming up today, we've got... oh, no, that is completely fried. Oh, scroll out, scroll in. There we go, it's all my slides. We have Put to the Test, a section with Nang Nang, talking about testing and talking about very, very unlikely events. We have some more curve sketching, because I've got some curve sketching left over from last week, where we had more curves that we wanted to sketch and not enough time to sketch them. And joining us in chat today are Lauren and Christian. You've already met Lauren and Christian if you've been watching the maths live streams. Lauren, you'll remember from Probability Theory a few weeks ago. Christian from Pigeonhole Principles a few weeks ago. They've been on the live stream before. They're also Oxford students, they're undergraduates, and they're in chat, so you can talk to them if you want to talk to them about Oxford student stuff, or if you want to talk to them about the maths that's on screen. Okay. Oh, yeah, Nang Nang, what college do you go
I'm at
to?
St. Hughes.
St Hugh's College, fantastic, great stuff. Okay, and I'm going to do shout outs to the audience very quickly. Hi Athena, hi Lucy, hi Dev, hi Athena again, hi Raphael. Is juggling one of the things that can happen? People are doing, at the moment, I think there's a theme just before
Not
we
on
went
my skill
live.
set. Is it
People,
yours?
people talking about other suggestions for the live stream. I've seen Will, James Maynard and Ben Green be in the What's on Your Mind series. So the What's on Your Mind series is going live on our main YouTube channel. We'll see who else is involved in that project as it goes on. Is it very laggy? Audio is great, but the screen is terrible. Ooh, okay, right, let's try de-lagging my computer a little bit. YouTube, I've got a YouTube error message as well. Right, okay, let's not worry about that. Let's assume that's all fine. Audio's fine at least, even if my screen is rubbish. Just chilling a bit. Wish I could stay, but you're doing the Somerville Maths Study Day. We advertised the Somerville Maths Study Day a couple of weeks ago. You can watch the replay. Yeah, so after we're live, it's going back. If you have any questions afterwards, you can email us on oomc@maths.ox.ac.uk. That goes to the Oxford Online Maths Club team behind the scenes. It's become okay. I think it's when I try to change slide or when I try to move the screen, it lags everything out. Okay, we're learning about the limits of my poor computer. Okay, I'm going to switch over.
Considering our format today, that might be a problem.
So we're using a slightly different slide format with lots of zooming in and out and moving around. So see how much of that we're going to get away with. Okay. Yeah, people are saying it's better now because I've been looking at this Lauren and Christian's names. I don't dare show you the next slide. Let's do an experiment. There's further reading for the live stream, each live stream, notes and extra stuff, things that we forgot to say while we were live. That's over on the Maths Club website. If you head over to maths.ox.ac.uk/r/club, that's where we're putting stuff up afterwards. I tend to upload that at some point on Friday, so if you check back at the weekend, then there might be more reading or exercises or homework problems. If you want to see that for a previous episode, then go to the website and click Read More for a particular episode to find out more about the topics that you saw there. That page has also got other resources and links to all of the previous episodes. Right, okay. I think that was the intro that I was supposed to do. I think it's going over to Nang Nang, and I'm going to try and find your bit of the slides over here. It's all like
should just be below.
There we go.
Okay. Hi all. So today we're going to be talking about hypothesis testing, which is one of the more important bits of statistics. In particular, if you scroll down a bit, we're going to be talking about this guy.
Here he is.
Yeah.
Did you draw this? Is this?
I did not draw this.
Okay.
That is his avatar, I'd say.
Okay. He's called Dream. I've not heard of Dream.
Well, he's a Minecraft streamer. He's quite famous, so over 18 million subscribers on YouTube. So I'm guessing a good chunk of you have probably heard of him, especially if you're into watching Minecraft on YouTube.
18 million is a lot. For reference, this channel has got 1,300 subscribers. I keep checking. Definitely not 18 million. Wow, okay, right. So he does Minecraft.
So we're talking about him today because he's landed in a spot of hot water. In that he's been doing a sequence of speedruns on Minecraft and has been getting suspiciously good luck.
Okay.
So specifically, he's been on Minecraft version 1.16 plus. He's been doing the any percent speedrun, which I learned just means that you don't really need to worry about achievements and all of the other myriad stuff you can do. You just need to finish the game. And glitchless, which is exactly what it sounds like. Don't use any glitches.
I'm trying to remember the most recent version of Minecraft I played. The 1.16 plus sounds like I don't know when. At some point,
I feel like this is a good point to give a disclaimer in that I have literally never played Minecraft.
Okay.
I've only been exposed to statistics here, so if I get things wrong.
Cool. Okay. So what's the point of any percent? He says, reading the screen very carefully. So he's just like two people who don't know about Minecraft speedrunning trying to explain Minecraft speedrunning.
Pretty much. Yes, there is the speedrunning little controversy. So what's the goal in the any percent? Well, basically, you need to kill a dragon and go into a portal.
Okay.
At least that's the part you do at the end. But in order to get to the dragon...
I remember the dragon. I played enough Minecraft that they added the dragon.
Yes. So one of the key bottlenecks is that you need to open the portal, which goes to dragon. And this requires a certain number of pearls and blaze rods. So ender pearls and blaze rods. The way you get these is random.
Okay.
So
you get blaze rods. I remember blaze rods. Sorry, I'm trying to make this about
blaze rods
me
you just get from literally killing blazes.
Yeah, in the nether, right? And ender pearls you get from killing endermen, right?
Yeah, there's multiple ways of getting ender pearls. But in terms of speedrunning, the way which is quick is that you trade with a bunch of piglins, which are these pigmen that you can find in the game.
So this is something they added after I stopped for a bit. So you give gold to...
So you give gold to these pig creatures that you might be able to see on screen now, and they have a certain chance of giving you ender pearls in return. So I think they give you maybe more than one ender pearl, but at least each trade gives you some number of ender pearls with this 20/423 probability. And we can be very exact about this because we can just look in the game code and see how it's coded. And this works out to be about 5%. Blaze rods are somewhat simpler. You just kill a blaze, and it has exactly a half probability of giving you a blaze rod, so exactly 50%.
Fantastic. Okay.
So, in his sequence of speedruns, Dream made 262 barters with these pigmen. So, with the probabilities we just gave, you'd expect about 12 successful barters, i.e. successful meaning that it gave you ender pearls. He got 42, which is quite a bit higher than you might expect. As for blaze rods, so 305, he killed 305 blazes. So you'd expect about 126, the closest whole number, but he got 211. So the fact that these are bigger than the average isn't in itself suspicious in any way. There are a lot of Minecraft speedrunners, so you do expect plenty of people to have quite good luck in the game.
Okay, I'm gonna pause here because chat is way ahead of us in ways that I love chat. Some people know where this is going. This story hit the news at some point a while ago that Dream did these speedruns, got these numbers, and then there was lots of controversy around this. You might have already heard about this. In particular, while we were planning to make a maths video going on live stream, going into this content in great detail, Matt Parker, who's great and amazing and everyone loves, made a very popular video on this topic already, and beat us by about a week and a half. But that's okay. Matt Parker's video is great. Somebody's linked it in the comments on chat below, and I think I'll add it to the YouTube description after the live stream, so that people watching back everyone can watch Matt Parker's video. It's a really good look at the maths. I've got Nalang on because I want us to talk about hypothesis testing. I'm going somewhere with this, I promise. That maybe you've already heard this story about dream cheating, but I want to talk about hypothesis testing in more generality. Okay, so we're going to talk about Dream a little bit, and maybe you've already heard about Dream. Maybe you're sick to death of hearing about Dream, but we're going to do the numbers just because it's fun to work out the numbers. We're going to do the numbers, and then we're going to talk a little bit more widely about hypothesis testing in a way that I haven't seen in the Matt Parker video, and I haven't seen elsewhere. Sorry, that's just a head off chat. Who some people in chat, or at least people talking about this. Yeah.
I've seen the word binomial, which is good because that's the next topic.
Yeah, it's time to introduce the binomial distribution, right?
Yeah. So the binomial distribution is when you do a sequence of independent trials. So what do I mean by independent? That means that the two things don't affect each other. So, for example, the outcome of, say, 2 random coin flips are independent of each other. If I get heads with one coin, it doesn't affect the probability that I then get heads with the other coin. The probability that I'm late to work and the probability that I wake up late in the morning, those two are probably more dependent on each other. If I wake up late, I'm likely going to be also late to work. So we have that, we're assuming here that each of these trades, each of these barters, and each of the dropping of blaze rods, these are all independent trials. And the question is, if you have, say, a general n number of trials, and each trial has probability theta of success, most people write this as p, but just to match with some notes I have later, I'm going to write theta for this. What is the probability that you get k successes? So we write this capital X as the total number of successes we get. In maths, it's a convention to write random things as capitals. So capital X is going to be random things, whereas the little numbers, these little k's, are just going to be normal numbers. And we want to look at the probability that we get exactly k successes.
Okay, so we've got n trials or attempts, so we'll be quite general about what those might be. And the probability is theta. I guess maybe at A level, people might be using p for probability. Can I ask why you're using theta? Is that...
Because initially because I think I had p's in other places and I didn't want to get too mixed up, but now there's not really a good reason.
Okay, cool. Theta probability. Cool. Okay. So I guess working out the probability like this, we need to think about what could happen to get exactly k successes.
Yeah. Well, so if you have a specific sequence, and this is an ordered sequence. So you do your n trials in specific order. And what's the probability of seeing a specific sequence when there are k successes and n minus k failures? Well, if the probability of something being a success is theta, the probability of it being a failure is 1 minus theta. So when we need to multiply them together, essentially, the events. And because this multiplication is, you don't care about the order, right? A times b is b times a. We can group all the successes together. This gives us our theta k. And then we can group all of our failures together. This gives us a 1 minus theta n minus k. Here's a little interesting question. Is there a metric for measuring dependence? There are many metrics for measuring dependence. So you have something called there's something called mutual information, which is about entropy and quite fun. But there are ways to measure how dependent two things are. Probably the one you might meet at A level is covariance,
okay, so
which is not perfect. So covariance talks about how closely 2 random variables vary with each other. So if they're in an exact straight line, you would expect that covariance to be either 1 or minus 1, depending on if they're negatively or positively, their correlation, which is dependent on their covariance. So you can talk about how correlated random variables are. This isn't perfect in that 2 things can be not independent and still have correlation 0. But if you go to uni, you can learn more about that.
That sounds like a fun kind of thing for counterexamples. So It seems to me that people at A level might learn about covariance, but they might not see the puzzle of trying to work out 2 variables that are not independent, but happen to have covariance 0. So maybe that's a puzzle for whichever section of our audience have seen covariance, to try and work out 2 variables that happen to have 0 covariance. Cool. A-level topics, nice. Somebody asks, what is n? N is the number of trials, so possibly the number of times you threw a gold bar at a pig, and k is the number of times that it gave you back.
It's a good question, yeah. So for our purposes, we are going to assume that n is just some number. The dream started off saying, I'm going to do this number of trades. this is somewhat not realistic because the number of trials you do depends on how lucky you get, right? If Dream had a particularly lucky run, he might say, well, I'm calling a quiz today. In which case, this n becomes random itself, and that does affect our modeling, which means that this binomial stuff isn't quite true, and we need to account for that. But that's not something. This is covered quite well in the paper that was released. If you want to read that, this is called optional stopping. We have a problem, I believe, later, which talks a little bit about optional stopping.
After the ad break, I've come up with a puzzle involving this kind of optional stopping thing. This kind of phenomenon that if you stop as soon as you see a success, or if you stop on some condition based on success, then you can slightly skew the results that you get in terms of these statistics.
Wrong thing. Isn't this a bit combinatoricsy? It is very combinatoricsy.
It's not abuse. I'm throwing the gold to the pig, not at the pig.
Oh, yeah.
Giving it to the pig. The pig likes the gold. I'm throwing it near a pig. It's fine.
It's a fair trade.
Oxford does not support animal abuse. Right, don't send a letter. Okay. Someone said this was getting a bit combinatoricsy. We've highlighted that.
Exactly, it is getting very combinatoricsy. So the point here is that we don't actually care about the order we see these successes and failures. So if we see a failure and then success, that to us, as far as the x is concerned, the total number of successes is the same as seeing a success and then a failure. So to account for this, we just sum up all the different ways to order the k successes and n minus k failures, since each of these events are what's called mutually exclusive from each other. So if you see one of the events, you don't see one of the other events. So you can just sum them all together, and they have the exact same probability as each other. So we just turns into a multiplication. We're not going to the combinatoric side of things today, but there is a notation for the number of ways to order k successes and n minus k failures, which is this n choose k here. So note there isn't a little bar between the n and the k. We're not dividing n by k here. This is what's called the binomial coefficient.
NCR for like n choose r. NCK for n choose k. And it's got some formula to do with factorials that you might know already. How do you highlight a message? That's a power that I've got on the live stream to highlight a message. Let's just assume it's magic. Cool. Yeah, someone's made Wilf has made a point about correlation and causation, but like, cool. Okay. You've got some notation that I think people see at A level, and I tend to not see in like Matt Parker's video to write this distribution for the binomial distribution. You learn this at A level at some point. This notation for writing, well, the number x is distributed like this expression. Okay.
It's a vector, it's not a vector either. This is just notation. So this isn't the two-dimensional vector nk. This is a specific number which is represented by the nk.
Yeah, I think maybe people. I'm going to write in some extra notation just in case.
Yeah. So N2C is probably more common in A level, but if you go to Unimaths, you see N2C less and less and less.
N choose K, and it's supposed to be the number of ways to order K successes and n minus K failures. Let's get that on screen. I can get that all on screen at once.
It's often called the choose function because another way to think about it is how do you choose K items from N items. But these turn out to be basically the same thing here. Would it be useful to use a normal approximation to the binomial distribution here? It kind of. You can use a normal approximation for the binomial distribution here, but the numbers are small enough right now that a computer can just chug through everything manually. So we don't actually use the normal approximation here. It's just.
So I suppose I've put in some formulas. So this number of ways to order K successes and n minus K failures is like if you have a list of some successes and failures, well, this factor in blue is supposed to allow for all the ways that if you want 37 successes, they might be in the first 37, the last 37, or a random 37 from the middle. And the number of ways to arrange those amongst all of the trials, it's a sort of standard combinatorics thing that you learn at some point in A level, I think, that's n factorial divided by k factorial, n minus k factorial, where factorial means multiply all the numbers going down to 1. And people are telling me about A level notation where maybe they write just B instead of bin.
Yeah, it's just notation. So some people write down the full binomial if they're particularly want to be specific. Yeah.
Tilde instead of equals, I guess, because x is... Yeah, there's some sort of philosophy here, right? That x is a random variable that could take lots of values. It could be 0, it could be 100. It's not quite equal to this thing. It takes values from some set with some probabilities. So it sort of follows. It's more like having a rule or a distribution for what x could be.
You might say it's distributed as a binomial, but you wouldn't really say it's equal to being a binomial distribution.
Lily's got a thumbs up for using the C button on a graphical calculator.
Yes.
If you type in
exactly
NCK, then you can work out the number of ways to order k successes and n minus k failures, or the number of ways to choose k things from n. Maybe we should do some at some point on the live stream. Might do some choosy sort of problems. That sounds like fun. This is not an equivalence relation either. Stands for can be more than good. Fine, sounds good enough to me. Okay, we've got some amusing pictures just to finish off the kind of dream story bit of this.
Yeah, very much. So now we have a formula we can actually plot these probabilities. So for us, our n is going to be the number of trials he did, which is like for about 300-ish. Theta for the piglin trades is that roughly 5% probability. And we're going to vary k and plot results.
So x is the number of successes, and my screen is freezing because I'm trying to show you graphics through an online whiteboard and it's not going very well. So down the side is number of successes. So thinking about how many times are you successful, and then the bars are different lengths for different probabilities. So see, I think this is 12 is the most successful, and there's some kind of nice distribution there. So 12 is the most likely, 11's not unlikely, 10, 9, fine. Dream is over here, which is sort of way off down that end. So this is kind of normal stuff happening, and then successes. 42 successes is way down over here. I've become very laggy, so I'm going to sit still for a moment. Ooh, actually dropped the stream for a moment there. Not sure if I'm currently live. Just going to assume I'm live. Don't swear or divide by 0. Okay, I'm going to wait for that to come back. Might be going, might not be. Who knows? Right, cool. Okay, very laggy. Come on, computer, you can do it. I believe in you. Come on, computer. Right, cool, good. I'm going to assume that sound at least is working. On screen now is a binomial distribution and a little orange arrow to show that Dream is way off to in the positive time. I mean, freezing a lot. Yeah, this is a bit much, maybe. Okay, I might switch tech after the app break. We'll see. Right, I want to get on to binomial distributions though, or hypothesis testing. Okay, we're gonna move on. I feel like that's for blaze rods. There's a similar sort of pattern. There's some distribution of what's likely, and Dream is way out over on the far out of one side, but much more likely. Freezing for a long time, not just when you started showing graphics. Yeah. Okay, right. I've got a plan. And student ambassadors have told me that I'm still live and they can hear me, which is nice to know. Thanks, Lauren and Christian. Super laggy. Right, okay. I'm going to see if we can get through this bit. And then switch tech. Fun. We're live. Anything could happen. Do you want to read out what's on screen? Because I think the audio is working even if the video is not.
Okay, sure. So you end up with these probabilities which turn out to be very unlikely. So the probability of getting 32 pill trades or bigger is about of the order 10 to the minus, I think it's 12. And it's the same for the piglin trade. So there's a number at the front, but when you're dealing with numbers this small, you don't really care what the exact number is. Just the power of the 10. That's all that really matters.
Okay. Cool.
And because in the code these two things are independent, so the blaze rods, the random numbers for the blaze rods and random numbers for the piglin bartering are independent of each other, the probability of getting both of these happening, we can just multiply them. And that gives us something of the order 10 to the minus 23, which is very, very, very unlikely. So Matt Parker is a good video here where he goes into just how unlikely this is.
Bro, okay. We're basically cutting out, so I'm going to try and fix the stream very slightly. Just in case anyone can hear, can you talk us a little bit through? So it's kind of the end of the dream story. This is insanely unlikely. This is a really unlikely thing to happen. I got you on because I thought we could talk more generally about hypothesis testing. I'm going to try and work out a good way to show that to the live stream. This might involve turning things off. We might disappear briefly. Yeah, okay, I'm going to turn some video stuff off. It's going to be fine. Yeah, okay. So you're still here, but I'm gonna cut like this, I think. I'm also gonna turn this off. Try doing this. Okay. We're gonna try doing that to save bandwidth. My video's disappeared. Yeah, basically unwatchable. Right. Okay. Good. So we've now got no video, but hopefully my computer is recovering and can at least show you the slides we've got. Oh, stream quality so bad. Oh no, that's mean. That's too mean. Okay, we can fix this. This is fine.
Okay, we'll go through it.
Let's talk to what we've got and see whether that works or not.
Sure. So the formal way you set up these kinds of tests is called hypothesis testing. So we're going to first think about what's called simple tests. I've written up this function f here, and f was just this probability we had earlier. So f of x, given depending on this parameter theta, is the probability that a binomial n theta random variable takes the value little x.
Okay.
And what we want to do is test on what the value of theta should be. So we have our null hypothesis. A null hypothesis is what you assume is true normally. It's the default state. So in our case, we're assuming it's going to be the value it is in the game. So for blaze rods, this will be a half. For the ender pearls, this will be about 5%. We're going to test this against an alternative hypothesis, which we write as h1. And this is that it is equal to some value which is bigger than theta naught. And for now, we're going to be thinking about some specific value. Right. And later on, we'll talk about how to talk about testing for a general greater than theta naught. So then, what is a hypothesis test? A hypothesis test is specified using what's called a critical region. So a critical region is just some subset of the possible outcomes which x can take. Right. So x can take values. In fact, that should start off at 0, not 1. But x can take values 0, 1, 2, all the way up to n. Right. And a critical region is a subset of these numbers, such that if we end up with a value inside our region, we say h0 is false.
Okay. So we reject h0 if it's in some sort of set. This is a general theory about hypothesis testing now.
Yes.
I'm slowly turning technology back on again to see how much I can get away with.
Okay. So yeah, this critical region determines the test in that if we reject our null hypothesis, if we land inside the critical region, and we accept our null hypothesis as long as we're outside of it. So how do we tell how well a hypothesis, how well a test does? Well, there are basically two ways in which a test can go wrong. Either h0 is true and we reject it, or h0 is false and yet we still accept it. Right? These are false positives and false negatives. So a false negative is when h1, or alternative hypothesis, is true, and yet we don't reject null hypothesis. This is called a type 2 error. The other type of error is called a type 1 error, which is where our null hypothesis is true, so the default is actually true, and yet we still reject it.
Okay, question in chat. Can we just use the assumption that θ1 is not θ0, rather than the case that θ1 is bigger than θ0? I think they say that's a two-tailed test rather than a one-tailed test.
So we'll talk about this a little later, but this sort of affects how we judge the error. So we see that the false positive the two quantities which are associated with these errors are called the size and the power. So if we scroll down a bit. So alpha, we normally use notation alpha for what's called the size of the test. And this is the probability, essentially, of making a type 1 error, of making a false positive. So assuming that our theta, our H naught, our null hypothesis is true, that theta is actually equal to this theta naught, what is the probability that we actually reject our test, that we reject our null hypothesis? The other quantity is called the power of the test. This is the probability of it going right when the alternative hypothesis is true. So if the alternative hypothesis, theta is equal to theta 1, is true, what's the probability that we do actually reject the test? And for good tests, we want a small size but a high power.
Okay, small size, high power. So size is a sort of mistake you make where you... Hang on, so type 1 error. So H naught is true, but oh no, you've rejected it. And and power is the probability of not making a type 2 error. Okay, there's sort of lots of this or not this, size or power, H naught, H1 stuff going on as well. Oh, what was that?
That's confusing.
Yeah. Top comment beneath me now is, why is it theta to the n minus x rather than 1 minus theta to the n minus x in that function that was on screen about 20 seconds ago?
I have likely written it incorrectly.
Could have been wrong, but it's not on screen anymore, so I think we might have got away with it if I hadn't read out this chat message.
Wait. If it's changed, then it's definitely incorrect.
Someone's done
It is definitely incorrect. It is definitely 1 minus theta, yeah.
Right, okay. So person in chat wins, right?
Yes.
Where was that? Up here.
So one thing to note here is that in order to talk about the power of a test, we do need to say what our alternative hypothesis is.
Right, okay. So this is, you don't know whether you've made a type 2 error or not unless you know what your alternative hypothesis is. Okay.
So I guess if we want to ask a question to the chat, can you think of a test which has size 0, which has perfect size?
Okay, let's remind them what size is. So challenge, can you think of a test that has 0 this thing, 0 probability of making a type 1 error when H naught is true? So if H naught is true, then if H naught is true, then your type 1 error would be if you rejected H naught by mistake. Oh no, terrible disaster. H naught and H1 here, I guess you could think of them being sort of statements about the world. So they're statements about they're kind of like your hypothesis, I guess. They're statements about what might be true. I guess we use P and Q.
So the standard courtroom analogy is H naught is sort of innocence, it's the default state, whereas H1 would be guilty. It's the thing we need evidence to convince ourselves of.
Yeah, these things are supposed to be alternatives, right? They're supposed to be one or the other, I think.
Yeah, so you can't have the two hypotheses overlap, otherwise you're not really testing anything.
Someone in chat has put jolly good recovery clapping emoji. They don't realise that clapping emoji takes more processing power than ASCII, so there's a chance that will destabilise the live stream again. So can we think of it? We've got a bit of lag on chat. But can we think of a test where a sort of way of doing testing? I'm not saying it right. Can you say it again? Sorry.
Can you think of a test which never makes type 1 error?
Oh right.
Which never falsely rejects.
So maybe not a kind of binomial test where you look up some numbers. That'll be a very careful test, right? Where you could go and look up some numbers, compare the probabilities, and say, oh, this probability is very small. That's one sort of test we could do. But that does make type 1 errors sometimes. That's sometimes wrong in that way. We can come up with a different protocol, a different plan of how to do our testing. So that we never make type 1 errors. Sounds too good to be true, right? Never making errors, that's what we want in mathematics, right? Never making errors. So there's going to be a catch. But we can avoid making type 1 errors.
So the test that would make sure you never reject falsely is the test which just never rejects. So no matter what happens, you always just accept your null hypothesis.
Right, okay. So if your testing process, this is separate from your hypothesis claims, separate from your claims about the world.
For a hypothesis test, you need 3 things. You need to say what your null is, what your alternative is, and what your critical region is. And in theory, you should do all of these ahead of time.
Right, yeah, okay, so that's a subtlety, right? That you've got 2 alternative competing worldviews about the world, but you also need to come with Also needs to come with a plan about how you're going to choose between them. JDS has got it. If you never reject, then you'll never falsely reject. Do I mean like a scenario? Yeah, I guess I mean, you can imagine doing this test. H0 and H1 could be any two opposite statements, like the sky is blue versus the sky is not blue, and my test is going to be look at the sky. And that does make some errors sometimes, I suppose, depending on whether it's nighttime and also depending on where the other sort. I find it really hard to judge what's a type 1 error and a type 2 error live, sorry. Yeah, so JDS says, if you never reject, then you'll never falsely reject. It is a trivial example, but yeah, that is all I agree with all of this.
I mean, although it's trivial, it sort of gets to the point at which that most tests sort of need to balance these two. So the issue with that test is that then it has quite low power as well. It's not a very good test. But what we're trying to do in statistics is, often the problem is, suppose we have a specified size that we want to be below, right? We want size to be small. How can we then optimize the power of our test? Which is the most powerful region for a specified size?
People are, due to lag in chat, and people are now suggesting a test where there's no critical region, right? So there's no way to, is that the right way around? No way to reject.
Yes,
H0.
you have zero way to reject. I mean, also you can have a very powerful test by just saying we always reject, but then it has a horrible size.
It's a little bit morbid, but someone is dead, and the test is an autopsy. Is that something also that's never going to reject? Well, I suppose there we need the kind of H1 to be the person is still alive. I don't really like this example. It's quite icky, right?
It's everyone.
Okay. Here's a big claim.
So if you remember these probabilities I had earlier, this is something which we're definitely not going to prove. It's got a fancy name, which is called Neyman-Pearson lemma. But it says that for any test which has size less than or equal to alpha, the critical region which maximizes power takes this form. So we look at our x, we evaluate this fx at theta naught, and we divide it by the value at theta 1. So what sort of is this quantity? Well, fx of theta naught is the probability that we actually take the value x at theta naught. And fx of theta 1 is the probability that we take the value x at theta 1. And this looks essentially at, are we more likely to take this value under theta naught, or are we more likely to take it under theta 1? Does that make sense? So if this value is, say, 1, then it's equal. Then both of these scenarios are equally likely under the test.
So I think I want to do a caveat here. This is a very general theory. This is not specific to tests like the binomial test. And it's not specific to tests where you do anything that looks like the binomial test. This is some sort of theorem from university statistics about all possible tests. So it's taking that scenario we just had, looking at well, how can you have good power while still having a reasonably small size? And there's some theorem on the screen, complicated, that says that the way you do that is to choose the critical region in this way. And it's astonishing that this works without doing some sort of binomial theorem maths, because it's not specific to the binomial theorem. This is some sort of general fact about how you should choose critical regions in general. You're going to show us what it means for the binomial, though, right?
Yeah, so I think it's probably best to actually talk about a specific example here.
Ooh.
I think my things have disappeared.
The brackets just went up. I don't know why. Do you want this bit? Or no?
Yeah, sure. So what are these values actually for binomial? Well, fx at theta naught. Writing is not going very well.
So this is the probability that you see. Sorry, this is the probability that you see x if theta naught is true.
Mm-hmm.
And this thing down below is going to be the probability that you see x if theta 1 is true. So in words, I suppose this is saying we're comparing, given our two worldviews, either h0, the sky is blue, h1, the sky is not blue. Those things each have some probability that we then go out and observe that the sky is blue, or elsewise.
Yeah, I agree. It's quite a lot of fancy symbols.
Yeah. And we haven't proved where the theorems come from. So in some sense, we are just throwing random university maths at you, but it's related.
Well, it's actually quite intuitive in terms of how it works, right? You're looking, are you more likely to see what happened under the null, or are you more likely to see what happened under the alternative? And if the ratio of these two gets too small, then you're saying it's much, much, much more likely to see what we happened under the alternative than it is under the null. And if that's the case, we should reject.
Right, so when you say that out loud, it sort of almost makes too much sense, right? Like you're comparing to say, just choose the one that explains your observations more, or something like that. And there's a lot of subtlety baked into how this critical region works and how this threshold value eta works.
Well, the eta you just pick, essentially, to get underneath our size alpha. So this is basically a tuning parameter, if you like.
Okay. So the claim is for any size alpha, the test for any alpha, the test with size at most alpha, so it might be better by having a smaller size, then the test with the highest power will be something like this. Take your critical region, the times when you reject H0, to be those observations where the kind of ratio of how likely it is that you see the observation is less than some critical value eta. And I'm freezing again. Okay.
Also, if you evaluate this ratio for our binomial, the binomial coefficient difference just cancels off. So we get a theta naught at the front, divided by theta 1. This is all to the power of x here.
So this is comparing two different binomial distributions to think about if the probability of success was theta naught or if it was theta 1, then those would give different probabilities for our actual observation, and we should look at the ratio of those.
And then we have the same for the 1 minus theta naught terms.
Yeah, I think this is true. The greater the value of eta, the more likely you are to accept. Or is it the?
Yes.
Yes. Okay.
So if you make eta really big, yeah, you'll often accept theta naught.
That makes your size larger as well, right? Because if you're more likely to accept your null hypothesis, then you end up moving towards that case that we talked about, where if you always accept your null hypothesis, then that's not very good as a test.
So if you just take out the stuff at the front, we get a minus theta naught. We get something which doesn't depend on our x, importantly. So it shouldn't really affect this ratio. It's just a number at the front.
Ooh, I think your handwriting's also going. Right, okay, maybe.
But importantly, we just get some number which is theta naught, theta 1, 1 minus theta 1, because there's a minus x for that power, so everything gets flipped. 1 minus theta naught. And this is all to the power of x.
Cool. So at the end of the day, this first thing is constant, and this part over here depends on theta naught and theta 1, or is it just an increasing function with x or something like that?
Well, so if theta naught is less than theta 1, this thingy in the middle is just a number which is less than 1.
Okay.
So if x gets big, this gets small. In particular, all I'm really proving here is that this is decreasing with x. So our critical region should just take the form, is x big enough?
Yeah. Okay. So eta doesn't quite work out to be the size at the end, answering this anonymous question. Eta is related to the size, and for different, if you're aiming for a different maximum allowed size, alpha, then you might get a different threshold eta. I think there's probably some complicated formula relating, if you have a particular size in mind and you're doing this sort of test, then your threshold eta should be this number. In practice, you need to do algebra like the algebra that's just disappeared off the bottom of the screen to work out what that cutoff threshold is. Okay. I quite like this. It justifies using this form of test where you only look at a kind of particular outcome or anything more successful than that. Is that right?
So maybe it's better if I write it slightly differently. In that this might be better written as saying we have this probability of x being equal to little x given that h0 is true on top, and we have this probability that x is equal to little x given h1 is true at the bottom.
Right, okay. So I think imagining this thing at the top as a probability given h0 and this thing at the bottom probability given h1, I think might link the notation back together again. Cool.
So you're dividing the probability that you see your random thing being what you actually observe if the null hypothesis is true at the top of the ratio. And at the bottom of the ratio, you're seeing the probability that you observe what you observe if the alternative is true.
So one last time for them, because somebody asked nicely. Let's wrap up by doing this statement of university stuff one more time. If you're going to go out and do a hypothesis test, and you're trying to design that test to make sure that you don't make too many type 1 errors, which is a sort of error where you falsely reject the null hypothesis when you shouldn't have rejected the null hypothesis. You don't want too much of that, but you still want some power to your test. You want to actually be right sometimes as well, in some sense, not make too many type 2 errors. Then the form that your test should take is always a bit like this, that your critical values, where you reject the null hypothesis, should all be those observations where the probability of seeing that under your null hypothesis is much less likely than your probability of seeing that observation under your alternative hypothesis. You should pick out those observations X where that ratio of probabilities is particularly small. Those are the ones where you should reject your null hypothesis. Those are the ones that your null hypothesis does a really bad job of explaining. So those are the ones where you should reject your null hypothesis and go for the alternative hypothesis as well. That's the best design that your test can have for a given size. And there is this interplay between size and power, but if you want to not make the size too big, well, the best you can do for the best power is to pick out the critical values of X, just like this. Okay.
Right. I think it's best if we just briefly mention the last part instead of going into detail, which is that, for example, for Dream's test, you don't have a specific theta 1 that you're testing against. You're testing against this general theta being greater than theta naught.
Okay.
And in that case, what you want is also something which is uniformly the best. So for all, if we do the previous calculation for all theta 1 greater than theta naught, we still want to be the best among all possible tests. And it turns out this is still possible and is given by the exact same test.
Brilliant. Okay, so this step that people do in their dream analysis where they say, he had this many successes, we're going to look at the probability that you get this many or more successes. That step of looking at this many successes or more is justified by that being the right sort of test to do to maximize power. Okay, so I wanted to show you this because it's a link back to explaining a bit of stuff in A-level maths, or a bit of stuff that's kind of hit the news recently, that there is some sort of university maths behind it to justify that step of designing this sort of test. And if you're interested in designing tests to catch people who are cheating, ideally you do it before the things hit the news and everyone's arguing about what test to use, but after the fact, you can still learn about testing as well. I'm going to run an ad break very quickly, and then we're going to talk about curve sketching. Thank you again to Nang Nang for explaining hypothesis testing. Thank you very much. Right, okay, I'm going to run the ad break. We didn't do one last week because we were doing loads of curve sketching. It's definitely going to freeze me. I'm also going to, this is slightly rude, I'm going to turn off your camera. You can hang around on the stream if you want to, and your audio is still working, but I'm going to turn off your camera. I'm really sorry. Thanks for coming along. I'm doing it to save bandwidth. Cool. Right. Okay. That might improve my computer. Okay. Ad break. Okay. I'm going to catch up with chat. Here's an ad break. I'll read out the problem as well. Ariana is experimenting. So Ariana's in this problem. She's experimenting with adding together consecutive numbers. So for example, 33 plus 34 is 67. That's the sum of some consecutive numbers. She's experimenting with other ones, and I've got this question for you to have a think about. What numbers can Ariana make? By adding together just 2 numbers, maybe adding together 3 or 4. Which numbers can Ariana never make with a process like this? Okay, just going to replay chat a little bit, talking about the lemma, talking about size. How difficult is it to get a first in maths at Oxford? Ooh, pretty tricky, because our exams are quite tough, but quite a lot of people in each year, I don't know the stat off the top of my head, but quite a lot of people in each year do really well in the exams, and we give them firsts. So not impossible, some of our students do get firsts, about 30-40% of them or something like that.
I mean, I'm not sure if you can answer this, but do you know if it's curved or not for Oxford Maths?
I beg your pardon?
Is it curved so that a certain percentage gets it each year?
Or is it... Not quite. So okay. Some people... Yeah, there's a rough sort of constant percentage, roughly. Cool, right, okay. People are saying thank you to you in chat. You're still here in audio, spooky audio only. Right, good, okay.
Impressed.
I need to do some curve sketching because we got it left over from last week. I'm going to try and do curve sketching on a computer that would quite like to have a break. So the air brake is mostly for the computer's point of view, so it can cool down a little bit. I
feel like it might be sensible for you to start a new Miro board.
That might be a good idea. Wonder if I can get away with that. Ooh. Yeah, there's a lot of stuff in this Miro board, isn't there?
Yeah.
Let's give it a go. Everyone's going to see my Miro account. No, actually, this doesn't work. I'm going to delete everything. Yeah, I'm going to delete everything. Okay, our break's going away. We're going to do some curve sketching. Oh, and people are answering the question on the board. I should leave it up because people are answering it. I don't think you make 2. I don't think you make 2 either. Because if you start adding consecutive numbers together, maybe you've got a 1 and a 2, and that's already too much, right? And if you've got 2 numbers, you have to make at least 3. You can make odd numbers, says Zach. That's true. You can't make an even number by adding together 2 consecutive numbers. That's true, and I think the same. You can't make even numbers by adding together 2 consecutive numbers. Well, I can make some even numbers by adding together more consecutive numbers, though, but I can't make 2. That's true. If I add together even 2 consecutive numbers, even just 2, and I pick the smallest ones I've got, 1 and 2, add them together, I've got 3. Cool. 2 numbers gives you odd. What does 3 numbers do? Right. Cool.
Is it first, second, or third for PhD? I can't answer this. You don't really get first, second, or third for PhDs anymore. You get what's called a Viva, which is a scary interview with people who know a lot more about the subject than you do, and they basically say how many things you need to correct in your thesis.
Ah, okay. Nice. Yeah, positive numbers only, please. So the problem for Ariana, you can think about a version with positive numbers or one where you're allowed to use negative numbers. If you're allowed to use negative numbers, then it turns out that the problem's not that interesting. Cool, right, okay. It's not so much my computer that's struggling, it's the amount of stuff I'm asking it to do. Okay, last time we were asked about this curve sketching problem, x squared e to the minus x squared. And several people contacted me on the email address below to show me their curve sketching solutions to this. The way I like to think about this is to think about really large x and really small x. 3 numbers will be a multiple of 3. That's true as well. That doesn't help very much for making all of numbers, but it is interesting that when you add together 3 consecutive numbers, you always get a multiple of 3. Can you prove that? Is that something that always works? Is that always true? Anyway, for this curve sketching, I'd like to think about big X and I'd like to think about small x. When x is really large, I've got this exponential, e to the minus x squared. That's tiny. So I've got x squared. X squared is quite big, I guess, but e to the minus x squared is really tiny. There's this fact I know that exponentials beat polynomials or something like that. That if you've got a very small exponential and a very big polynomial, then the exponential kind of wins, and I get something very small. Okay, very small and positive. I guess that's an observation I can make, that this is positive. Cool, okay. So I think this is positive and very small when x is large. So let's draw this decreasing from whatever. Excuse me. When x is very small, I think I know that when x is very small, e to the minus x squared is roughly e to the 0, which is 1. So this thing, I guess, there's not quite rigorous expansion, but e to the minus x squared is about 1. X squared is, well, x squared is about x squared. So this thing together is about x squared, it turns out. So y, I think, maybe looks a bit like x squared when x is small. Okay, so I think it maybe looks a bit like this for small x. I'm going to try and join the dots. And people emailed me, Kevin, if you're watching. Kevin emailed me to say this is an even function, which is a great observation. So this is the observation that x and minus x give the same y. That's one way of saying it. Have I done BMO to get into Oxford? You don't have to do BMO to get into Oxford, obviously. It's not part of the admissions process. It's a set of interesting maths puzzles that some people in the UK do. That means that this is supposed to be the same on the other side. Okay, that's basically enough information by saying small x does one thing, large x does another thing, in between something else.
I think it might be worth saying that if you're struggling with BMO, you can still... BMO content is very specific. So university maths is a lot more than just what's on the BMO. So even if you struggle with BMO and you enjoy maths, you definitely should still apply.
Links to material like that in the resources section on the maths website if you want to see stuff like that. Okay. Yeah, Hannah says, I think they use a variation of that function to model the Maxwell-Boltzmann distribution. They do. In fact, this is the distribution. This is the distribution. Oh, come on. We can do this. Distribution of speeds of a particle in a sort of, I guess, like a 1D gas or something. There's something weird going on here as well, I think. I think it's something like that. A 1D gas, the gas can be left or right, random motion, Brownian motion stuff going on. That's my understanding anyway. There's some distribution of speeds in a particular distribution at a particular temperature. Wavehands, thermodynamic physics at a particular temperature. Cool. And some of the parameters in here depend on the temperature. Cool. Right. Okay. People are proving that if you add three consecutive numbers together, call them n, n plus 1, and n plus 2, and when you add them up, you get 3n plus 3, which is a multiple of 3. Fantastic. I love that. I love that people are doing the question alongside. The next part of the question was, what happens when you add together 4 numbers? Which is less obvious. You might like to call them n, n plus 1, n plus 2, and n plus 3. Cool, okay. The other thing we wanted you to sketch last time as a kind of homework was this thing, y equals e to the x over 1 plus e to the x. And here you can check some sort of special values, check what's going on when x is 0. When x is 0, you get y is 1/2. I guess there are other values I can plug in, like x equals 1, but then I get loads of e's everywhere, and I don't really want to think about that. I think I also want to think about what's going on when x is very large. When x is small, it's close to 0, it's close to 1/2, seems fine. When x is very negative... Come on, computer, it's 5 more minutes, we can do this. When x is very large and positive, I think e to the x is huge. E to the x is much bigger than 1. So this fraction is going to be roughly, e to the x on the top. That's absolutely huge. On the bottom, I've got 1 plus e to the x, which is some fraction which is going to be about 1, I think. As a question for Nang Nang in chat, which was, how many hours of work do you do every week as a PhD student? Do you want to answer that one on air?
Well, actually, yeah, I suppose. It's about the same as... what you find is you have a lot more than just research to do at PhD level. So teaching becomes something you need to do a lot of. And a lot of admin stuff. But I think basically the same as a 9-to-5 job, same as most people. That's when the offices are open.
I did my PhD a bit like a 9-to-5 job.
Yeah.
I know other people who put more time in and got more done during their PhDs, let's be honest.
Yeah. I mean, it's up to you, sort of.
But in terms of thinking of it like that. Cool, okay. So this function that I've been sketching on the board, e to the x over 1 plus e to the x, is a sigmoid activation function. Yes, this person in chat, sigmoid activation function. We said last week that it was something to do with neural nets, maybe it's falling out of fashion, I don't know. It switches nicely between 0 and 1, so that as you increase x, it kind of smoothly switches from 0 to 1. So if you can use for kind of binary signaling or something. So that if you've got some signal, maybe some chemical, that's affecting whether or not your neuron fires. I am alternating between neural nets in computers and neural nets in your brain. If you've got some chemical that changes whether or not
they're related.
Cool. Yeah, cool. And it's a perfect sketch here because I put one half near the middle but not quite, to show that it's a sketch, not an actual, so that you know it's not an output of Desmos or something like that. Right, cool, okay. One of these came up in my PhD. I don't have time to explain where, but it turned out that I was looking at velocity in a fluid. I was doing a fluid dynamics problem, and it turned out weirdly that the velocity in a thin layer there was high at one end, 0 far away, and it did a nice sigmoid in between, which is nice to see. My A levels were maths, further maths, I think physics, and then I think I did a bit of chemistry alongside as well. And my university offer did not involve chemistry A level, at which point I was doing chemistry for fun. Cool, right. Is this distribution related to your PhD? Someone said, because I mentioned last week that it was. This distribution is related to my PhD. Or maybe they mean the previous one. The previous one I know nothing about. This one, oh, this one's related to my PhD. But I don't have time to say now. Right, cool. Maybe we'll do that next time. In the further reading, I'm going to put a problem about optional stopping bias, so you can explore that if you want to think about the previous thing. If you want to think more about sigmoid activation, then that'll go in there. Maybe I'll put a bit in about my PhD fluid sigmoid activation thing. Maybe not. I'll put some hypothesis testing facts in there. Thanks again to Nang Nang for your presentation on stream. I'm sorry about the tech problems that froze up
Thanks for
most
having
of
me.
it. And thank you to Lauren and Christian in chat as well. It's been quite an emotive one. Oh, just in time, someone said adding up 4 numbers gives you 2 more than a multiple of 4, which is great news. We can make numbers like 26, like that was the example earlier, which is 5, 6, 7, 8 added together. 2 more than a multiple of 4. Brilliant stuff. Earlier someone said you can't make 2, which is 2 more than a multiple of 4, so I guess that's an exception. There are some other numbers you can't make as well. I'm going to leave that as an exercise for you. We'll see you again in 167 hours for the next episode of Oxford Online Maths Club. Stay safe. See you around. Bye.